that is speed of sound. Speed of sound V is given by Newton, found it by dimension analysis. It is E upon rho, where E is the modulus of elasticity for air and rho is the density of air. But one of the important assumptions of Newton's formula is V equal to this much. But his assumption was there is no change in temperature when sound wave travels through the medium. That medium remains at isothermal temperature. There is no change in temperature, means delta T equal to 0, or we can say it is isothermal. Means for isothermal we can say for any gas it is constant, for air also it remains same. On differentiating we can say PdV plus VdP equal to 0, means P equal to minus VdP upon dV. And later on next articles we study elasticity. In that way we can say this is the bulk modulus of air. This is bulk modulus of gas, we can see, that is P. Hence, in this equation if we substitute speed of sound equal to P upon rho of air, then again pressure is nothing but the atmospheric pressure, that is height of a mercury column into density of a mercury into g of gravitational acceleration and rho for air. On substituting these values, all the values are known to us. Height is 0.76 meter of Hg, or simply 760 mm of Hg, into 13600 kg per cubic meter is the density of mercury, and G value is standard, that is 9.8, and upon density of air is 1.293. On solving we found that this is 279.9 meter per second. By Newton's formula this value we got, but actual value is different. It is about 330 meter per second, means there is about 16% difference. This was difference definitely because of something wrong in the formula or something wrong in the assumption what you did. Later on, Laplace did the correction in this formula. It is very intellectual matter. First of all, you observe that Newton assumption was delta T, means when sound travels at that time there is no change in temperature of the medium. But as we see, there is compression, rarefaction observes. At that time, during compression, there is increase in the pressure. Therefore, there is a possibility of increase in temperature. There is rarefaction. At that time, there is a decrease in pressure. There is a possibility of decrease in temperature. Means there is constantly variation in temperature. Here the temperature is higher, but here the temperature is less. Then Laplace has thought that there is no isothermal condition, but the heat remains constant. Delta is equal to 0. And this condition is called as a isothermal condition. Isothermal condition, for this, from thermodynamics, we can say that PV raised to gamma equal to constant, where gamma is the ratio of two specific heats, that is Cp upon C. Cp is the amount of heat required to rise the unit mass of a gas through 1 degree when pressure is kept constant and volume is allowed to change. And Cv is the specific heat of a gas. It is amount of heat required to rise the unit mass of a gas through one degree when volume is kept constant and pressure is not changed. You can see in thermodynamics, Cp is greater than Cp. And this ratio for air is roughly or nearby 1.41. If we differentiate this equation like this, you will come to know that this gamma P equal to minus V dP upon d, and that is elastic constant of the air. Therefore, this equation becomes V equal to square root of gamma P upon rho. On substituting these values, we can say gamma is 1.41 into H is 0.76 into 13600 into 9.8 divided by 1.293, and this value comes to 331.5 meter per second, and this gives exact agreement with the practical values. Therefore, Laplace's correction is more accurate than the Newton's formula. The basic difference between these two is Newton assumed that there is no change in temperature, but Laplace has said that there is a change in temperature, but there is no change in heat content of the medium through which the wave travels. And therefore, the correct formula is this one. This is Laplace's correction.